In section 5.2, we're going to formally define what an integral is. First, what I'd like to talk about is net area. Recall when we compute an integral, what we're doing is we're computing the area between the curve and the x-axis. Well, let's just say that the area we're computing is above the x-axis. Well, if it's above the x-axis, then when we compute the area, it'll be positive. But if the area is below the x-axis, when we compute the integral, then it's going to be negative. I'm going to call this green area R1, and this is R2. Whenever we compute net area, now I'm not saying area. Area is always going to be greater than or equal to 0, but net area is going to be our integrals, and they can be 0, they can be positive, they can be negative. So when we compute the net area, what we want to do is we want to add anything that's above the x-axis, so any area above the x-axis. We're going to subtract the area of anything below the x-axis. So again, this is our net area. And this is going to turn into our integral, which again can be negative, it can be positive, it can be 0. What I'd like to do is go back to our Riemann sums, and let's just discuss the Riemann sum a little bit. Remember what we were doing with our Riemann sum? We were summing or adding up the areas of rectangles. So remember, this would be the area of one rectangle, another rectangle, and so on. So we're adding up the area of these rectangles, where f of x would be, say, the height, and delta x would be the base, or you can do a length times width. I'm going to go ahead in this graph below. I'm going to go ahead and partition into two rectangles. Why don't I just do a right Riemann sum? So if I were to estimate this area by using two rectangles on my integral from a to b, notice that the area wouldn't be accurate. Let's look at what happens as we make smaller and smaller rectangles. And I don't mean smaller, I mean skinnier rectangles. So what if instead of 2, what if I had really skinny rectangles? And I filled in this whole thing between the curve and the x-axis with these really skinny rectangles. Well, can you see that if I filled this whole thing in, that this would be a really accurate approximation for the area? And that's where our integral comes from. What we're going to do is, and instead of saying delta x, I'm just going to call it delta. What we're going to do is we're going to say, okay, what happens as the delta? Which when we say delta, we're referring to the width here. What happens as that gets smaller and smaller and it gets closer and closer to 0 in our Riemann sum? Again, all that means is that we're filling in our area, and we're approximating our area with these very, very skinny rectangles. So it's going to be an accurate approximation. So if we take the limit of our Riemann sum as these partitions get smaller and smaller and smaller, that's going to be equal to our integral. So remember, the integral symbol is this weird looking S. That's because it stands for sum. Now I'm summing from a to b. So I'm going to put the interval that I'm summing on. This integral symbol says I'm going to sum from a to b all the rectangles with f of x. So I don't need all that x sub k star, f of x, which would be the height. And instead of delta x, going back to our linearization, recall we talked about differentials, and differentials are very, very, very small delta x's, which is what we're doing here. We're looking at that delta as it gets closer and closer to 0. So I'll replace delta x with dx. Okay, so this is going to be a sum from a to b on my interval of rectangles that have a height of f of x and they have this base of dx. So at first it seemed like this integral notation was actually making things more complicated, but it actually isn't. It's simplifying everything. If we look down at this box below of our definition of a definite integral, all we're doing is we're replacing all of this Riemann notation with the limit, and we're substituting in our integral notation. So it's actually very nice. So a is called the lower limit of integration, and b is going to be called the upper limit of integration. So let's say that you have an expression and it's written as a Riemann sum. How do you change this to an integral? Well, first in example 1, it's saying that we're going to express this definite integral on the interval from 0 to 5. So a is 0, b is 5. This is going to be the integral from a, oops, why did I write a? 0 to 5. And our function is going to be what's inside the parentheses here. But when we write it in function notation, we don't need to write x sub k star. We just write x. So this becomes in parentheses 7x minus 3x to the third. And then we replace this delta x sub k with our dx. Sometimes people get lazy when they're writing out their integrals and they forget the dx, but that's really important because remember that's the width of your rectangle. So if you leave off the dx, you don't have a rectangle. Let's talk about when a function is integrable. So let's say that your function is continuous. You're done. Then you can find the integral. However, even if the function is not continuous, you still may be able to find the integral. You just have to make sure that the function is bounded. And when we say bounded, we're talking about the y values. We want to make sure our y values do not go off to negative or positive infinity, so no vertical asymptote. So either your function has to be continuous or bounded with a finite number of discontinuities. In the below graph, let's start with an a and a b. Let's say that I want to integrate, so find the area between the curve and the x-axis. Well, this first piece, why don't I call this C? Clearly this is not continuous, right? Because I have these discontinuities. And I'll call this D. I clearly have discontinuities, but that's okay because this is bounded. Notice there's no vertical asymptote. My y values don't go up to negative or up to positive infinity or down to negative infinity. So it is integrable. I do have a problem though. If I were to compute the integral, I would have to do this in pieces. So it's okay if the function is discontinuous. You just have to make sure when you compute your integral that you break it up. So I'll call this f sub 1. This will be f sub 2 and f sub 3. So if I were to compute this integral of all these three pieces, which clearly I can, right? You could clearly see the area. Then it would be the integral from a to c of my f sub 1 of x dx. That would give me the area of the first piece. And this is net area. It just happens that this function is above the x-axis, so it will turn out positive if I do compute it. But we're not going to compute it because I really don't have a function. From c to d, this is going to be f sub 2 of x dx. And then the last one would be from d to b of f sub 3 of x dx. So if there's discontinuities, you got to break it up into separate integrals. For now, what we're going to do is we're going to be using geometry to evaluate the definite integrals, and then we're going to look at properties to evaluate our definite integrals. And then in later sections, we'll just go ahead and we'll integrate it in a different way. In example 2, it says to use geometry to evaluate this definite integral. That means you have to graph the function, this integrand, which is the absolute value of x minus 2 minus 3. Well, I know I'm going from -1 to 8, so I think I'm going to put my axis probably about here. Let's see, so I got a -1, 0, 1, 2, 3, 4, 5, 6, 7, 8. I think I got it all. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So you could plug this in a calculator. You could just remember that the absolute value function is a v, and when x is equal to 2, that's when it's going to be equal to 0. But then it's shifted down 3, so you could do transformations. But what I'm going to do instead is I'm just going to plot some points. If I put in -1, because that's where my integral starts with, it starts with -1 and then it goes to 8. So at -1, this function is -3, absolute value is 3, it's 0. At 0 we have -1. At 1 we have -2. And is that right? At -2 we have 4, -2, +2, it's 0, -3. Yes, okay. And then it comes back up. And then it keeps going up. So here's my graph. And you're always looking at the difference between your curve and the x-axis. So from -1 to 1, 2, 3, 4, 5, this would be our region. It would be below, right? And then from 5 to 8, the graph goes above the x-axis. So, oops, I want to use a sharper piece. So that would be this region here. So the green region falls below the x-axis. So that's going to be, this is net area when we evaluate definite integrals. Remember, we're looking at net area. So I'm going to have to take this r sub 1 and make it negative, and then the r sub 2 would be positive because it's above. Well, if I look at r sub 1, that's going to be the area of a triangle with a height of 3 and a base of 6. Is that right? 1, 2, 3, 4, 5, 6. Yes. So the area here is going to be 1/2, base is 6, height is 3, and it looks like it's going to be 9. Well, the area of region 2 is also the area of a triangle where we have, and these really should be, where we have a base of 1, 2, 3, and a height of 3. The area of this triangle is going to be 1/2 times 3 times 3, oops, can't write today, which would be 9/2. So the definite integral, which is your net area, would actually be the integral is actually going to be a -9 because it's below, plus a positive 9/2, which would give me a -9/2. So the net area can be negative. Net area is integral. Area cannot be negative. So just be careful about what you're being asked to find. On the next page, we're just going to be looking at a lot of properties. Some of them are the same properties we had with indefinite integrals. If we look at property number 1, and this is important, it comes up, that if your limits of integration are the same, then the integral is 0. In property 2, if you want to change the order of your limits of integration, so here this is from B to A, then all you have to do is take its negative and change the order of the limits of integration. Property 3 and 4, that would be the same thing that we had for indefinite integrals. Whenever you're adding or subtracting, you can break it up into 2 integrals. Property 5 is a property we had with indefinite integrals as well. It says that if you have a constant, you can bring it out in front. So again, this is a property we had previously with indefinite integrals. And now any integral, any definite integral, can be broken up into pieces. So if you're integrating on some interval AB, you could pick any number C, and C doesn't have to be within the interval AB, it could be any number, and you could break up your integral into 2 pieces. 7 says if the integrand f of x is greater than or equal to 0 on your interval, then the integral is also going to be greater than or equal to 0. And that makes sense, because if your function is above the x-axis, then the integral would be positive. Well, let's say on some interval AB, we have 2 functions, f and g, and f is greater than or equal to g on that interval. Then when you integrate, that will also be true. The integral of f of x is going to be greater than or equal to the integral of g of x. This last property just says that if you take the absolute value of the integrand, then the integral will be greater than or equal to 0. So that's something that you can do if you're trying to find the area and not a net area. You can just make your integrands positive. Let's look at example 3. And example 3, in the box, I have 3 definite integrals. And I know what they're equal to. Notice I didn't give you the function f or the function g. All I did was I told you that the integral from 0 to 4 of f of x is -5. From 0 to 10, it's 12. And then the integral from 0 to 10 of g of x is 3. So let's see if we can use our properties to evaluate these 4 integrals. In the first one, what I notice is that it's going from 4 to 0. But I need from 0 to 4. So that looks like I can use property number 2 and take the negative of this integral to change the order of the limits of integration. So it becomes 0 to 4. of f of x dx. And I know that that's negative 5, so this becomes negative 5. Or just positive 5. The next one's a little bit tricky. It says we're going to evaluate the integral from 4 to 10 of f of x. But if we look at the two examples above, I have f of x from 0 to 4 and 0 to 10. Okay, so what I'm going to do is I'm going to be using property number 6, but backwards. If I take 4 to 10 and I add it to 0 to 4 of f of x dx, then that would give me the integral from 0 to 10 of f of x dx. So in this equation, all I have to do is take this integral from 0 to 10 of f of x dx and subtract the integral from 0 to 4. So if I subtract the integral from 0 to 4, then what I'm left with is the integral from 4 to 10 of f of x dx. This would be equal to 0 to 10, that would be 12 minus negative 5. And I get 17. In the next example, I'm adding f of x and g of x, and I'm looking at the integral from 0 to 10. So I don't know what f of x plus g of x is, which means I'm going to break this up into two integrals. 0 to 10 of my f of x dx, and then I'm going to add it to the integral from 0 to 10 of g of x dx. This would be 12 plus 3, which gives me 15. In the last one, I'm doing f of x minus g of x, which that's not really an issue, but notice my limits of integration. It goes 10 to 0, not 0 to 10. So the first thing I'm going to do is take the negative and switch the order on the limits of integration, 0 to 10, and this would be f of x minus g of x. Okay, something I do have to keep in mind is that this negative applies to this whole integral. So if I use property number 4 to split this up, this is going to be a negative, in parentheses, the integral from 0 to 10 of f of x dx minus the integral of g of x dx, all in parentheses, which gives me the integral of 12 minus 3. Okay, that would be negative 9. And that's it. So we're done with 5.2.